Yeah, I did that.
Okay, because they, I mean, there were still questions going on at that time, but I don't know if that means she didn't get her. Because Lee took this group and then I took over here, but when I got in there, it was already on to her. Okay. And then all of these guys were lines. Yeah, I took a picture of the screen. But,
Yeah.
useful that's gonna be. And then they only had like 2 minutes at the end, so Gloria didn't, she wasn't up there anyway. She was in B, but you know, at the table with us with the microphone. So I know they wanted to get a shot of her. So yeah, what I heard was really good. So yeah, okay, awesome. Okay.
Gonna be next, so
You're
showing how
next?
this one is.
So you are Seraphim Falterman? Seraphim, is that, am I pronouncing that correctly? Falterman, okay. I'm Erika. You have quite a title as well. It's always the goal.
Hello? Yeah, this one works.
Hello, welcome to part 2 of the water treatment session. I'm Erika Young, the moderator. I'd like to first introduce Yazeed Algurainy from NC State, who will be speaking on improving desalination in the electrochemical technology capacitive deionization using asymmetric electrode mass ratios.
Thank you so much, Erika, for the lovely introduction. That'll be good. Good afternoon, everyone. This is Yazeed Algurainy, a PhD student at NC State University, working with Dr. Douglas Cole. And in this presentation, I will be talking about a simple strategy to improve the long-term stability of anode and desalination performance in capacitive deionization using asymmetric electrode mass ratios. I know some words might be not familiar for some of you. So first of all, for those who are not familiar with capacitive deionization or CDI, it's a promising desalination technology for brackish waters because of its low energy consumption and selectivity for ions. So in CDI, cell voltage or current is applied across a pair of porous carbon electrodes so that ions in solution, for example, you have sodium and chloride, cations and anions, would be removed by the electrode of opposite charge through electroabsorption and storage within electrical double layers. So as a result, we have treated water produced at the effluent. So if you would sample the effluent solution for salt concentration, typically what you would see adsorption cycle, absorption phase, where the effluent salt concentration would be lower than the influent. And when the electrodes are supersaturated with the ions, typically the electrodes are, is it working? Okay. Typically the electrodes are short-circuited so that the adsorbed species during the adsorption phase are released and collected as a prion. So in CDI, the adsorption and desorption phases are repeated over and over again. So cell stability is very important to ensure a sufficient salt removal system. So those cycles are repeated over and over again. However, in reality, the story is different. So this figure shows the conductivity profile of our charging and discharging over 48 hours of continuous operation. And you can clearly see that after a few hours of operation, something is happening. You can clearly see the decline in salt removal after a few hours, indicating that there is a severe decline in desalination performance. And that's due to the corrosion of carbon, because again, the electrodes are basically made of activated carbon. So one result of, or one consequence of corrosion is a decline in desalination performance in the long term. Another consequence of corrosion is the increase in anode resistance. So anode is going to be the electrode that's positively charged that would be removed for anions like chloride. So this figure shows the electrode resistance. So remember, CDI, we have two electrodes, the anode and then the cathode. So this figure shows the resistance of the electrodes after CDI cycling. And you can clearly see that there are two orders of magnitudes increased in the anode resistance compared to the cathode electrode, which was stable and comparable to pristine condition before operation. Another consequence of corrosion is shifts in a parameter called the potential of zero charge, EPZC. So EPZC basically is electrochemical surface property that determines the capacity of electrodes to adsorb charged species. So in this figure, the EPZC, it's determined from the capacitance versus potential profile. And then the EPCZ of pristine carbon before CDI cycling, it's about negative 200 millivolts. It's a potential at which the capacitance of electrode is minimum. Due to cycling, when carbon oxidized, negative surface charge forms in the electrodes. That would result in a positive shifts in the potential of zero charge. So after 50 cycles, there will be a positive shifts in that electrochemical surface property. I know this might sound complicated, but I will make sure it's simple enough. So let's say we apply a cell voltage. So each electrode would be charged at certain potential. So you can see that the blue profile before operation, the capacitance is about 1.4 greater the capacitance of the electrode after operation. So due to cycling, we are basically reducing or losing some capacitance of the electrodes to remove charged species. As a result, you remember that decline in salt removal over time. That's due to losing the capacitance of electrode over time and due to corrosion of carbon. So the big question that we had is, what's driving corrosion in the long term in CDI? So remember, in CDI, you apply cell voltage or current, so there has to be some sort of cell voltage distribution across the electrodes, the cathode and the anode. So this figure shows the distribution of cell voltage across the cathode electrode at the bottom and in the anode at the top. And you can clearly see that over time, there will be a positive shifts or positive drifts in electrode potential. What that means is the anode electrode at the top, over time, will be exposed to highly oxidative potential in the long term. That highly oxidative potential is basically causing corrosion of carbon. So here we go. We have high oxidative potential. So the stronger driving force for carbon oxidation that would result in corrosion of carbon. So one question that we had is there a way to control the way the cell voltage is distributed across the electrodes? So again, is there a way to control how the cell voltage is distributed across the electrodes so that we can minimize the positive drifts in electrode potential in the long term? Now we will put CDI aside and talk about supercapacitors. So supercapacitors is basically a system for energy storage. So in supercapacitors, it was found that the cell voltage distribution can be controlled by varying the mass ratio of electrodes. So this figure shows the distribution of cell voltage across two electrodes with different masses. So the positive electrode in this case has smaller mass compared to the negative electrode, the anode. So remember, the positive electrode is the anode where I showed you there is oxidation in that electrode. In this case, because of the asymmetrical mass ratio of electrodes, the cell voltage that applied to the cell was distributed such that most of that voltage falls in the electrode with a smaller mass to compensate for charge differences. So when you apply cell voltage, the cell would be distributed to make sure that the electrode with a smaller mass has much greater charge density than the electrode with the smaller mass. Again, to compensate for charge differences. Now, on the other side, look at what happened to the distribution of cell voltage when we make the electrode with greater mass as the anode. So in this case, the cell voltage would be distributed such that most of that voltage would fall in the cathode. So in this case, this potential would fall in the anode, the electrode that exposed to high oxidative potential. So the question that we had is, can we use this strategy to avoid the positive shifts that I showed in the previous slide in the electrode potential over time? By adding more carbon to the anode. So we will go back to a CDI now. We assemble a CDI cell with 1-to-1 mass ratio of anode to the cathode. We apply 1.2 volts, and then we measure the cell voltage distribution over time in the anode and in the cathode. You can clearly see that there is a symmetrical distribution of cell voltage because the mass of anode to the cathode was 1-to-1. However, you can see there is some sort of positive shifts in the electrode potential that we have it here. Now, look at what happened when we added more carbon to the anode. Now we are limiting the cathode. The cathode would be the electrode with the smaller mass. The electrode potential, the green profile, shifted to more negative values. We added more carbon to the anode now, so the mass ratio of anode to the cathode was 3-to-1. By doing so, the electrode potential were further driven more negative. So what that means, at the anode, in each of those cells, the anode was exposed to different level of oxidation potentials because of the negative shifts that we added by controlling the mass ratio of electrodes. So what this means is, because the anode was exposed to specific oxidation potential, we evaluated the stability of anode due to changing the potential of the anode in each of those cells. So after 48 hours of continuous operation, we took a representative sample of the anode in each cell, And then we run some surface characterization of the anode after operation. Remember, we wanted to check the resistance that I showed you, the positive shifts in the resistance, and also the EPZC and salt removal as well. So we measure the EPZC, and then compared to the pristine that was not operated, relative to the pristine, the anode EPZC in all of the electrodes actually shifted to more positive values. However, that change was dependent on the mass ratio of electrodes. The anode in the cell with 1:1 experienced the greatest change, indicating that the anode in this cell, the 1:1, the conventional system design actually experienced much greater corrosion compared to the other cells, or the cell with a modified cell voltage distribution. We run EIS measurements to measure the anode resistance. So basically here you can see the arc in the impedance spectra. The arc represents the charge transfer resistance. So when anode corrodes, the resistance between the anode surface and the working solution would increase. So you can see now the red profile, which was the cell with 1:1, experienced more changes in the anode resistance compared to the cell with asymmetrical mass ratios. We run XPS measurements to measure how much carbon we have before and after the treatment. When carbon oxidized, the carbon content would decrease and oxygen content would increase. So with XPS measurements, we determined oxygen to carbon content. So relative to the pristine, oxygen to carbon content increase in all configurations. However, the cell with 1:1 mass, where was no modification of the cell voltage distribution, experienced the greatest change in oxygen to carbon content, indicating that we are losing carbon of the electrodes that we started with. So all those results suggest that because the anode was exposed to different level of oxidation potential, the stability of anode improved by adding more carbon to the anode and avoiding the high oxidative potential at the anode. Now, when carbon oxidized, in the long term, the salt removal would change. So we measured the salt removal in the three configurations: the cell with 1:1 mass, anode to the cathode, and the cell with 2 times greater in the anode mass than the cathode, and then the cell with 3:1 anode to cathode mass ratio. In the short term, the cell with 1:1 mass ratio, the red bars, the salt absorption capacity was slightly greater than the other cells. That's in the short-term cycling. However, over time, you can clearly see that the red circles, actually, there was a clear decline in salt removal compared to the others. Another example is the cell with 3 anodes and 1 cathode. And you can see in the short term, even though that cell produced the lowest salt removal in the short term, however, it maintained the more stable salt removal in the long term. And then by the long-term operation, that cell produced the highest salt absorption capacity. With salt absorption capacity measurements, because several ions present in solution, we don't know which ion contribute to the decline in salt removal. We measure chloride removal in each of those cells. And then in the short term, the cell with 1:1 mass ratio, the cell that exposed to greater rate of carbon oxidation, in the short term, it produced much higher chloride absorption relative to the cell with 3:1 mass ratio. However, that cell actually experienced severe decline in chloride removal compared to the cell where we modified the distribution of cell voltage across the electrodes. So in conclusion, we propose a simple strategy to control the distribution of cell voltage across the cathode and the anode. With this strategy, using activated carbon with no chemical treatment, we can actually minimize the high oxidative potential at the anode. By doing so, we improve the stability of anode in the long term. Minimizing corrosion at the carbon improved chloride removal in particular. Now I focus on the anode. and then reactions at the anode, but also the cathode electrode that was exposed to highly negative potential. Further research is needed to study the further reactions at the cathode. One example would be hydrogen evolution, because this could possibly impact the removal of sodium in the cell, and then overall would decrease the salt removal in the system. With that, I would like to acknowledge the collab at NC State, my advisor, Dr. Douglas Cole, and my research mate, and then funding agencies, King Saudi University and North Carolina State University. With that, I'm happy to take questions.
Thank you. We have a couple minutes for questions, and if you will, use the mic if you have a question.
Were you charging and discharging the capacitor each time, and how were you getting the sodium? How did you remove the sodium and chloride from your anode and cathode, or did the sodium and the chloride remain on the anode and cathode all the time? Did it just build up?
Okay, so
I don't understand the basic process. I understand cathodes, anodes, capacitors, AC, DC voltage, charging a capacitor, discharging a capacitor, but I don't understand how you got it out of the system.
okay, that's a good question. So first, there will be physical absorption in the electrode without any electricity being applied to the cell. So there will be physical absorption of the carbon to the charged species. That's physical absorption without electricity being applied. Okay. Now, when we apply electricity, we create a potential difference across the electrodes. So we charge the electrodes. So the electrodes are charged. One is going to be negatively charged. So the sodium would be removed by the electrode of opposite charge. So in this case, it would be removed by the cathode. Okay. Now, once the electrodes are saturated with ions, we reverse the polarity of the electrodes. We reverse the charge.
So you're running AC.
Yes, we reverse the charge, and then
Okay,
electrodes.
got that.
Okay, no, we reverse the charge.
You just showed a battery and the current going one way, but you're running AC.
Yeah, we run AC. Okay, sorry, we run AC, and then the electrode, the adsorbed species are released back into solution when we reverse the polarity of the electrodes.
So it goes back into solution.
Yeah, it goes back into solution.
Do you flush it out?
Yeah, the continuous flow
Okay,
flowing from here to there. So there are two phases, charging and discharging.
right.
Is that clear? So there are two phases.
But it could go back and forth constantly and not get out of the system.
No, because of the direction of the flow, we are pushing the solutions this way. So it would move with the flow.
Okay.
Sorry, I think we're out of time.
Okay.
Maybe you guys can continue your conversation.
Okay.
I'd like to introduce the next speaker. We have Seraphim Falterman, also from NC State, and his talk is thermal hydrolysis and anaerobic co-digestion of biosolids and grease interceptor waste, approaches for higher methane production.
All right, are we ready?
Yeah.
Excellent. Well, good afternoon, everyone. My name is Seraphim Falterman, and I'm excited to speak to you today about the application of thermal hydrolysis and anaerobic co-digestion of biosolids and grease interceptor waste to drive higher methane production in our anaerobic treatment systems. So some major questions that I'd like us all to be able to answer by the end of the presentation are, what is grease interceptor waste? Where does it come from, and how can we treat it? And then also, what is thermal hydrolysis and how does it affect anaerobic digestion? And finally, why would multiple feedstocks be combined in anaerobic co-digestion at all? And before we get too deep into the presentation, we need to situate ourselves where we are and what we're doing. So we find these processes in wastewater treatment plants or water resource recovery facilities. And we're treating biosolids. That is the material that is created through treatment of wastewater. And as we pull all the things that we don't want to discharge into our lakes, rivers, and streams, they end up in the biosolids. And once we create them, we still have to treat them so that they are safely managed. And the treatment system that we're going to use is anaerobic digestion. It's a treatment system driven by a complex consortium of microbes of many different species that are able to work in an oxygen-free environment to break down complex organics to smaller and smaller pieces until they're ultimately released as methane, that is biogas, and carbon dioxide. This process is sequential, which means that it cannot go any faster than the slowest step. And for us, that is going to be hydrolysis, that is the breakdown of carbohydrates, proteins, and lipids. We'll find that these lipids are particularly difficult for anaerobic systems to break down because it requires a microbe with a very particular skill set. That is, it needs to be able to produce lipolytic enzymes that are capable of breaking down a lipid. And there are just fewer species that have that capability. So digestions loaded with lots of lipids have a smaller team that is already at the rate limiting step. So we'll see the consequences of that later. But first, we need to talk about fat, oil, and grease, or FOG for short. This is a waste stream primarily associated with cooking. So after you render grease out of a piece of meat or have some oil and you pour it down the drain, it finds its way into the sewer system, where it coats sewer walls and saponifies, that is, it coats and hardens on the pipe walls, restricting flow. This accumulation of layer over layer can ultimately block flow altogether. And with nowhere else to go, sewage ends up in places that we don't want it, i.e. overflowing in an event called the sanitary sewer overflow. And the reason that this is such a big problem is it exposes communities to pathogens and pollution, as well as being unsightly. We have a number of these sanitary sewer overflows in the United States that are responsible to fog blocking. And the picture that you see here on the left is a fat bird pulled from the London sewer system. And they pulled 130 tons of similar material out of their sewers. We also have fog deposits in the United States, and it cost us $25 billion to remove them. It's an expensive endeavor, but we have to do this because the alternative are sanitary sewer overflows, which are problematic for the reasons mentioned previously. That expense prompted us to develop a strategy to keep fog out of the sewer. And that is to require actors that produce lots of fog, like food service, to install grease interceptors. The grease interceptor works by taking advantage of grease's tendency to float to the surface of a liquid. Everyone knows this from cooking. When you boil pasta, you see the oil rise to the top. Water that goes into this concrete box slows down as it has to fill the whole volume of the box, giving grease time to rise to the top. And as a secondary consequence, solids that have a specific gravity higher than water precipitate out to the bottom. The water travels under the bathroom wall and then enters the sewer system with much of the fog removed. Once the grease interceptor is pumped out, the waste product that is produced is called grease interceptor waste, and we produced a huge amount of it. Here in Wake County, we produce almost 19 gallons of grease interceptor waste per person per year. And if we think about this on a national scale, it's almost 6 billion gallons of grease interceptor waste. So we have lots and lots of this lipid-rich, energy-dense waste stream that we have to figure out something to do with. And I'm going to mention again its 3 layers and their tendency to separate immediately after mixing is stopped. This makes characterization of the waste very difficult in the lab, and loading of reactors very difficult because of the waste tendency to split into the 3 sections and difficulty in measuring it. But that difficulty is just part of working with grease interceptor waste and is well worth access to the energy density of the waste. Moving forward, I want to mention thermal hydrolysis. One of the reasons that this research was undertaken is because here in Raleigh, we're building a full-scale thermal hydrolysis plant that is designed by Combi. The way this works is a feedstock is pumped and held on deck in the pulper just below boiling. And then when it's ready, it is loaded into one of these pressure vessels here. They're heated by direct steam injection from the boiler to tremendous temperature and pressure. This is designed to break down those complex organics and lyse cells, that is, rip them open so that their nutrients enter the soluble phase. And that is in hopes of overcoming hydrolysis of the rate-limiting step of anaerobic digestion. Much of the feedstock that is in this tank remains in the liquid phase despite being well above the boiling temperature at atmospheric pressure, and it's kept in liquid phase by the intense pressure holding it and preventing it from boiling into steam. When the treatment is over, a release valve is opened and the contents of the pressure vessel is released into the flash tank. This release is not driven by just the pressure difference, but once the pressure is removed, the liquid that was kept in the liquid phase is allowed to boil. So the expulsion is violent and has very, very high shear forces, which help to further lyse cells and mix things into the soluble phase. To simulate this at the lab scale, we have a process that heats to similar temperatures and holds at the same time, though we are not able to have the steam rapid release step. But the goal is the same, to break down those complex organics into their soluble phase and lyse cells. A good indicator for success of this process is solubilization of solids, that is, the transfer of the feedstock portion that was a particulate into the soluble phase. And the reason this is beneficial is because microbes can much more easily access those nutrients when they're soluble, and this lets them eat faster and eat more, which drives higher methane yields. But we have to be careful when we're getting into such high temperatures because we can start the formation of inhibitory compounds as well as the release of a lot of ammonia and nitrogen. Of the inhibitory compounds, there are many, but the most important are the products of Maillard reactions, melanoidins. They're complex polycyclical organics that are very difficult to degrade and toxic to many microbes. Interestingly, the Maillard reaction is the same reaction that allows us to put a nice sear on a steak. And just as our doctors might tell us that those browned bits of steak aren't particularly good for us, they're not good for microbes either. Before we get into our results, I want to talk about substrate to inoculum ratio briefly, because our first round of testing is to decide what substrate to inoculum ratio to use in the second round. Substrate to inoculum ratio varying allows us to ask the question, what happens if we were to feed the microbes in our inoculum a different amount of food? So we do this by characterizing the amount of energy in the microbes. You can think about it as calories, though we use chemical oxygen demand. And a substrate to inoculum ratio of 1 is an equal number of calories internal to the microbes that are doing the work and to their food. And then these other treatments have less and less. In the subsequent slides, I'll call them a feeding of a small, medium, or a large. Here we see a trial of different substrate to inoculum ratios in thermally hydrolyzed biosolids. We have time on the x-axis in days and cumulative methane production on the y-axis. We'll see that as we feed a small, a medium, and a large, we get more and more methane, though it's important to note that the difference between a small and a medium and large is different. The small to medium jump is much bigger, whereas the medium to large is smaller. This is a different story than what we see in the effects of varying grease interceptor waste feedings. Similarly, we have time and cumulative methane production. We see with a feeding of a small, this blue trial, we get a stable methane production that is much higher than the biosolids from the previous slide. Note that the y-axis, only went to 60 in the previous, and this one goes all the way up to 350. And then looking from small to large, we see that the large was too much. It got into inhibitory concentration of grease interceptor waste and resulted in unsuccessful digestion. And the medium is an interesting phenomenon in that there is a variability. We have this outlier that performs less than the small feeding, and then 2 trials that perform more. This lets it know that when we're thinking about how much we're feeding in the subsequent trials, grease interceptor waste is what we need to worry about. And we chose a medium feeding because of this ambitious but interesting behavior here. So that's why we chose that and for the subsequent experiment. Now, looking to the first of our results from the second phase, you can see the successful application of thermal hydrolysis to biosolids. A similar graph as the previous few figures, we we have inoculum only control that's producing a little bit of methane, and then raw biosolids is producing more, which makes sense because they're being fed. And if we feed that same amount, that same calorie introduction or chemical oxygen demand introduction, we get twice as much methane out of the system, and it's produced at a rate 8 times higher. For some clues as to why these process improvements are happening, I'll call your attention to this figure here on the left. So we have total solids, volatile solids, and COD, and then their axes on these two sides. But I want to call your attention to the volatile solids, particularly this part here. You see in brown, we have particulate or suspended solids. And in the blue, we have soluble. And you can see that we transfer more than 2,000 milligrams per liter of the particulate into the soluble fraction with our thermal hydrolysis treatment. And that increased amount of easy to access food is one of the reasons that the process improvements we see on the right. Once again, a different story with grease interceptor waste. I want to call your attention. The red line here is the same inoculum only control from the previous figure. In the second trial, all of the trial versions were loaded with the same inoculum source. So you can think of them as the same team playing different matches. So they're very comparable in their microbial community. You'll note that raw grease interceptor waste fed to this trial reduced or resulted in less methane production. That is, the inoculum would have produced more methane had it not been fed at all. When we look at the thermally hydrolyzed grease interceptor waste, we see some process improvements associated with thermal hydrolysis, like increased kinetics, increased methane yield, but it's still overall an unsuccessful digestion. So this is the story of strong inhibition. I should point out that this may be due to inadvertent overloading while following our lab procedures for handling grease interceptor waste. It is just one of the difficulties of working with it. But for further investigation, I'll call your attention to this figure on the left. Similarly, look at the volatile solids. But different from the biosolids, we start off with a large soluble fraction that is destroyed by thermal hydrolysis almost completely, as well as a portion of the particulate solid. So thermal hydrolysis affects grease interceptor waste very differently. It has a destructive effect on the solids and the energy content that is inside of the grease interceptor waste, perhaps due to its higher lipid content, but more tests are needed to fully understand the chemistry that's happening within the thermal hydrolysis process in grease interceptor waste. As we transition to our examination of our co-digestion performance, you'll note that this figure on the left has all of the trials that we've seen in the previous two figures, as well as two new ones, a green that is thermally hydrolyzed biosolids with raw grease interceptor waste, and a brown that is thermally hydrolyzed biosolids and separately thermally hydrolyzed grease interceptor waste combined into a co-digestion trial. We'll note that both of these trials vastly outperform every other trial in the second round of experimentation, suggesting that there is something to combining these multiple feedstocks that allows us to access the high energy content of grease interceptor waste and helps us transform it into methane. Though the clear top performer is when both substrates are thermally hydrolyzed, showing process improvements such as shortened lag period, high production rate, and high total methane yield or maximum methane potential. Another thing to call your attention to are high theoretical methane potential recovery. That is, you can calculate the theoretical amount of methane that is possible to be generated. And we do this by only including the substrate energy content and then comparing, what we expected to see. And in both of these trials, we're seeing more methane than was in the energy content of the substrate, which suggests that something about these co-digestions helps access the methane potential, not only of all of the substrate, but allowing the community to get into the energy content of the substrate. And it's important to note that these are extraordinary claims and should be taken with a bit of an explanation that grease interceptor waste is very difficult to load, and they may have inadvertently been overloaded just because of the difficulty of characterization of the waste to plan and then the difficulty of loading the waste. So we may see in our subsequent analysis that we're working on now that this falls below 100%, but with such a high recovery for the thermal hydrolysis of both substrates, it's unlikely that it will fall all the way below 100%, though we will see in subsequent data analysis. Beyond the extra methane that co-digestion can produce and be used to recover cost in the wastewater treatment plant, we can also generate Class A biosolids because of the excellent pathogen destruction effect of thermal hydrolysis. This can help water resource recovery facilities achieve their goal of transforming waste products into value-added products. And both methane can be used on site or sold, and Class A biosolids can be sold to recover costs. During this presentation, I hope that I've made the case to you that grease interceptor waste has unrealized potential for green and sustainable generation of biogas and deserves further investigation, and that thermal hydrolysis has a role to play in that investigation and can drive higher methane yields and improved kinetics, especially when applied to co-digestion, in which it intensifies anaerobic digestion with process benefits like greater biogas production, shorter lag periods, and the possibility to generate Class A biosolids. Thank you so much for your attention. Are there any questions?
Thank you. We have about 2 minutes for questions. I have one. So does this mean that now that we have ways to hopefully digest this fog, that should not reduce our individual counties' push for us to not put grease down our drain?
No. We absolutely need to avoid putting grease down the drain. That is not what this is to say. Any grease that you put down the drain will combine with ions in the sewer and harden. This is to say that food services have and that collect this and, let me run back way to the beginning. These grease interceptors are maybe 1,000 gallons or more. So there is a huge amount of grease in there. In fact, if you came off the highway to get here, all the fast foods you pass, there are several grease interceptors in the ground. They have to be, and because we have to divert fog. But at home, you should put your grease in a can and save it. You should never pour it down the drain.
Our county gave us boxes and bags to roll up our
Those were
grease.
great as well. Any way that you can divert the grease out of there. So if you get to reuse a can before recycling it to hold the grease, would be great. If you have a bag that your county gives you, also a great solution, but it definitely needs to be diverted from the sewers.
Awesome. Thank you so much. Oh. We have about 20 seconds.
Oh, so thermal hydrolysis seems to be expensive. And is it very doable for like large scale treatment for grease waste? Is there any alternatives that's cheaper?
There are alternatives. Some people try to compost it and some people try to use it as a soil amendment, but those processes are difficult because of the high energy content and the tendency of the grease interceptor waste to coat things in a lipid layer that prevents oxygen introduction. And for the energy recovery part, their full-scale systems have a recycle that allows recovery of heat, and they are much more efficient than our lab scale one. It's just because it's scale.
Thank you.
Thank you.
To introduce our last speaker, who is virtual, Mr. Dale Cobler, who will be speaking on the tools for drinking water reuse and treatment, aluminum sulfate coagulation optimization for ultrafiltration membrane pretreatment using raw surface water blended with ultrafiltration permeate.
What was the speaker's name?
Dale Cobler.
Hmm.
I think I'm saying it correctly.
Dale, are you there?
We chatted, yes.
Are you able to share your screen?
He's under attendees.
Yeah, he should have access. There you go.
Sorry about that. Are you folks pulling up the presentation from that end?
Yes, one sec. I just have to share your video too as well. One sec.
Okay.
All right, you good to go?
Okay. All right, folks. Afternoon. I know that title is a mouthful. I'm going to quickly present on coagulation optimization for a drinking water treatment plant that is using both conventional and membrane treatment technologies, as well as recycling backwash water that would otherwise be discharged to a wastewater treatment facility or to a local body of water via NPDES. Two Rivers Utilities, abbreviated as TRUE, is a public utility located in Gaston County, North Carolina. The water treatment plant has a treatment capacity of 27.3 MGD. It receives raw source water from Mountain Island Lake, which is a part of the Catawba River Basin. Mountain Island Lake provides a stable, consistently lower turbidity raw water supply for this treatment plant. And the plant provides drinking water to approximately 100,000 people across 7 municipalities. The TRUE water treatment plant operates both conventional granular media filters and ultrafiltration membrane systems. There are 2 conventional plants that each have 4 granular media filters. There are also 2 ultrafiltration membrane systems. One of those is used to produce permeate for distribution, and the other is used to recycle spent filter backwash water. The spent filter backwash water is waste that is generated from cleaning both the conventional and first stage membrane filters. A documented challenge with recycling spent filter backwash is the propensity of this waste stream to contribute to the formation of disinfection byproducts. We will discuss a little bit more of that next slide, but the conventional filtration treatment and ultrafiltration membrane systems, they're primarily independent of one another up until the filtration step. The conventional and UF membrane permeate is blended to provide finished water for the distribution. So this is a key consideration for how the efficiency to remove unwanted matter in one system can influence the other. The primary source of the compounds needed to form DBPs is natural organic matter. Natural organic matter compounds in natural waters are generally grouped into 2 categories. You have autochthonous, which are formed in the body of water, and allochthonous, which are formed in the soil or formed in upstream bodies of water. NOM can further be characterized generically as humic or non-humic. Humic substances typically include humic acids, fulvic acids, humans, which are generally high molecular weight. Non-humic substances such as carbohydrates, proteins, and peptides are typically low molecular weight and found in lower concentrations in most natural waters. So disinfection byproducts are compounds that are formed when a disinfectant containing chlorine is used and reacts with that natural organic matter during the disinfection treatment process. So DBP formation is influenced by NOM, bromide concentration, chlorine dosing, pH, temperature, and detention time. Humic substances absorb UV light at 254 nanometers and have been positively correlated with DBP formation. Therefore, the humic portion of the NOM can be reasonably identified using UV absorbance testing at 254 nanometers. This would be the UVA 254. Specific UV absorbance, or SUVA, is a measure of dissolved organic carbon aromatic content that it's calculated by measuring the DOC and UVA 254 of a filtered water sample after removing total suspended solids. SUVA values greater than 4 generally represent a sample composition of hydrophobic aromatic compounds, which are humic, whereas a SUVA value less than 3 typically identifies a sample containing more hydrophilic or non-humic compounds. TRU's water treatment plant often has SUVA values below 3, which suggests the latter more non-humic NOM in the raw water source. DBP concentrations have regulated limits established by the EPA for drinking water. The TRU water treatment plant kept their DBP concentrations within regulated limits, but had observed an uncharacteristic increase in the distribution system samples. One of the potential contributors to DBP formation for NOM reactions during the disinfection process. UVA 254 data needed to be collected throughout the water plant to better understand the efficiency of the NOM removal and where opportunities might exist to improve coagulation. The hypothesis was that the organics in the first stage UF membrane system supply water could be reduced by introducing optimized aluminum sulfate coagulation as a pretreatment. This project involved data collection in the TRU water treatment plant that was operating in real time. It was critical to collect as much data as possible to be used for the experiment design and decision-making. The first part of this project focused on UVA 254 data collection to better understand the organic matter that was present at different stages of the treatment. This data was collected weekly, and it was trended to identify if additional organics removal was necessary. After approximately 90 days of UVA 254 data collection, the laboratory staff completed a series of jar tests using the first stage ultrafiltration membrane supply water to establish a dosage range where alum could be used to target the removal of organics. And that data was used to establish the final set of jar testing experiments. It was necessary to establish sampling sites, as mentioned before, throughout that would represent the organics removal at all the different stages of the treatment. Because it is effectively 4 plants in one, that can be a little busy. The conventional and ultrafiltration membrane combination at the TRU water plant has locations where these systems function independently and where they are combined. So special care was taken to identify similar locations for each system where the samples could be comparable in treatment terms. Sample 1 and sample A are the same for conventional and first stage membranes. Samples C and C1 and C2 are on the conventional filters are comparable to sample number 5 on the first stage membrane system. So both of these samples are essentially filtered water from each system. Samples D1 and D2 represent the conventional filtered samples, which are C1 and C2, combined with the first stage membrane permeate, which is sample number 5. that has been treated with post-filtration chemicals and is sent for storage into clear wells before being pumped into the distribution system. TRU has 2 clear wells that are operated in series, with D1 being the first and D2 being the second in terms of sampling sites before that water is pumped out into the distribution system. The overall sampling sites permitted a good generic overview of the treatment process and where the UVA 254 was at each place. Those samples were collected between January and June of 2021, and a separate field study was completed in the distribution system to assess DVPs that was independent of this project. So just a standard jar testing preparation to show methods here. 1 liter of a 1% stock solution of alum was prepared. Alum, aluminum sulfate, is a commonly used cationic metal salt coagulant for conventional drinking water treatment. Alum hydrolyzes quickly into water, forming insoluble precipitates that destabilize the particle via adsorption and charge neutralization. Making a 1% stock solution just simplifies the jar testing procedure. Sorry, moving a little quick to make up some time here. The jar testing experiment was completed 3 times with different concentrations of 2nd stage ultrafiltration membrane permeate blended with raw source water from Mountain Island Lake. The typical ratio of this permeate to raw water that is blended for supply water that goes to the 1st stage membranes is 15% permeate to 85% raw water. So 10, 15, and 20% permeate blended with raw water was selected for the jar test experiments to best represent the operational conditions in the water treatment plant. And currently the 1st stage membranes are not operating mixers, so I was not able to mimic those conditions perfectly in this experiment, but this could be used to put into action. This graphic displays the mean UVA 254 values for all of the samples collected over the approximately 6 months of 2021 at the designated sites. So if you look at samples 1 and sample A, those are actually equivalent samples. That's the raw water supply. The conventional treatment is all of the letters on the right side in this graphic, A through C1 and C2. And then the membrane side is samples 2 through 5. The conventional treatment plant averaged a 72% removal of organics through the normal coagulation, flocculation, sedimentation, and filtration processes. If you look at sample A, and then you look at samples C1 and C2, that's after the treatment happened. And then the 1st stage ultrafiltration system averaged a 52% removal, samples 4 and 5 as the feed water, and then sample 5 is after the treatment occurred. This graphic is showing 5 weeks of initial UVA 254 sampling, where the stage 1 UF supply water or feed water sample, this would be the green sample number 4, was collected. This sample was not collected beyond the first 5 weeks as it did not have an easily comparable sample in the conventional treatment process and as a result of some staffing limitations. Sample number 1, which is the darker blue at the top, is the raw water source and is the supply water to the conventional filtration system. Samples C1, the light blue, and C2, the orange, were both located in the conventional system and reflect filtered water post-coagulation. The conventional treatment plant demonstrated consistent removal of organics from the raw water. The C1 and C2 samples are comparable to the sample 4, which is again the green line, in the 1st stage UF membrane plant. However, the supply water to the 1st stage UF membrane system is a blend of 85% of sample number 1, which is the dark blue line at the top, with 15% of sample number 3, which is the red line, which it does fit in there as you would expect. So sample 4 should be influenced by the organics that are located in samples 1 and 3. Lastly, the UVA 254 distribution values reflect the blending of the conventional samples with the first stage UF membrane permeate. The distribution values are higher than the conventional filtration, while the first stage permeate was higher than the distribution. It can be deduced that lowering the UVA 254 values of the first stage permeate would result in a lower distribution organics concentration. The UVA 254 samples were collected between January and June of 2021. This graphic specifically looks at the membrane treatment system over a longer duration than the last figure. We can see that the second stage UF permeate, sample number 3, consistently demonstrated the most removal of UVA 254. This sample is then blended with the raw tap, which is sample number 1, to provide supply water for sample number 4 to the first stage UF membranes. Both UF membrane systems demonstrated consistent removal of organics despite variability in the feed water, and is evidenced by the permeate samples for both of those, which are samples 3 and 5 respectively. However, it is noted that the removal was still less than that of the conventional filtration treatment. This figure displays all 3 of the jar tests that were completed. The red and blue bars are the turbidity values, as noted by the scale on the left side of the graphic of the jars, both before and after the total 2 hours of settling time. If a coagulant is effectively working, then we would expect to see a decrease in turbidity values as more of it is added to the water until it reaches a maximum removal potential. Improper alum dosing can result in flocculant not settling, in which case we would expect to see higher turbidities. Additionally, alum is an acid with a pH around 3.5, which will lower the pH of that blended sample, which is usually between 7 and 7.3. The pH range of the water is important to the efficiency of the coagulation. Historical particle charge neutralization for the true water treatment plant determined via particle charge analyzer has indicated that alum optimum coagulation range is usually between 6.4 and 6.7 on the pH scale. And the green line represents the measured UVA 254 value of the coagulated and settled samples. And what we can see is there's a clear direct correlation between turbidity and UVA 254, which would be expected. The 10% jar test had an optimum coagulation dose of 7 milligrams per liter, whereas 15 and 20% were 8 and 9 milligrams per liter, respectively. UVA 254 sampling and analysis identified a consistent trend where the conventional treatment with alum coagulation removed more organics than the UF membranes do without alum coagulation. There's an opportunity to introduce alum coagulation pre-treatment to the first stage ultrafiltration membrane system with the goal of achieving similar organics removal to that of the conventional plant. An additional benefit is that this could be accomplished with less alum dosing than the conventional treatment process, and it includes recycling of spent filtered backwash water. The true water treatment plant could continue to optimize the alum coagulation process by collecting and analyzing more relevant data. This could result in additional organic matter removal and potential cost savings.
Dale, let me interrupt. We are going into a break, but that is our time for this session. I know you started just a little bit late, so if anyone wants to hang out and continue chatting with Dale before our next concurrent session begins at 2:45.
Sorry, my next slide was the question, so we were done.
Okay. Sorry, thank you. So let's thank Dale before we have questions. Any questions? Okay, we have one coming.
Okay.
Hi, Dale, thanks for a great presentation. Forgive me if you answered this in the beginning of your talk, but I was wondering why you chose to use alum as opposed to ferric or some other polymer. What's the advantage of alum as your starting point?
Excellent question. It was a more practical one. It's we currently use alum at that drinking water treatment facility, so it was readily available. And we also have There's already pumps that are set up to dose into sedimentation basins there. So it could be something that would have been capable of applying very quickly.
Anyone else? All right, well, let's thank Dale again, and that concludes our wastewater treatment part 2 session.